All right. Good morning. How are you doing today? Doing good? All right. So my name is Fasih. I work as a developer advocate for StarTree. And the topic of my presentation is how you can build a real-time data platform using Kafka, Debezium, and Apache Pinot. So before we get started, I have a quick question for you. Let's do a quick show of hands. How many of you move data from transactional databases to analytics databases? Just put your hands up. So that is a few number of people. I was expecting a whole lot more. But anyways, hopefully by the end of this talk, I would have convinced you that you can unlock a whole lot of value if you move data from transactional databases into analytics databases. And it's even better when you do that in real time. So what are we going to cover today in this talk? We'll start with the motivation, why you would want to move data from transactional to analytical databases in real time. We will look at technologies that would enable you to do this. We'll look at the design of the system. And finally, we'll have a small demo which shows you how this data can actually be moved. So let's start with the motivation. So imagine a typical scenario. You have a whole bunch of microservices. Each one of these microservices has its own database, and you'd like to derive insights from the data that is stored with your microservices. So what you can do is you can move this data to a central location, such as an OLAP store, uh, and that is where you would run your analytical queries. So imagine you have an e-commerce service. An e-commerce service has microservices for placing the orders, for maintaining the inventory, for user profiles and such. So if you're trying to find something like the product that is trending, you would have to join the data from the orders microservice with the products microservice, right? The name of the product comes from the product service, and the orders probably just have IDs for the products that were ordered by the customers, and you want to join those. And the best place to do that is in a central OLAP store. So how would you go about moving this data? Well, there are two ways you can do this. First is you can move this data periodically in batches, or the second is you can move this data continuously as streams. Okay, we'll look at each one of these. We'll start with the first one, which is how to move data periodically. So when you move data periodically, you move data at regular intervals, right? 1 hour, 6 hours, once a day. This is classic ETL, but it's slow. It introduces delays, and there are a couple of ways you can do this. You can either move all of your data every single time you want to load this into your OLAP store, or you can only move the data that has changed. Okay, so that is the classical ETL method. But there is a way in which we can do this in a much better way, and that is to move data continuously as streams. What this does is it moves the rows, but instead of moving those rows in batches, it moves them one at a time. As soon as a row is inserted or updated in the database, you can take that row and you can ingest that into your OLAP data store. Okay. And this is what we are going to build, as we will see in the demo. And hopefully I would have convinced you that this is fast and that it allows you to derive insights in a matter of milliseconds. So why would you want to do this? Why would you want to move away from your classical ETL where you load rows in batches, and why you would want to move towards moving them as streams? Well, the reason for doing that is because data has perishable value. Okay. And as time passes, the value of that data goes down. So imagine, still staying with that e-commerce example, imagine you're running a sale and so some products are being ordered more frequently than the others. Knowing what those products are and making sure that those stay in your inventory so that people can continue to order those, that lets you take action on your data as quickly as possible, right? If you were moving this in batches and you found this information 6 hours later or 12 hours later, well, a lot of time would have passed and you really wouldn't be able to act on it because your window would have gone out. So having looked at why we would want to move data in real time, let's look at the technology that will enable us to move this data in real time. So Debezium, Kafka, and Apache Pinot are the technologies that we would look at that would let us move this data in real time. We'll look at each one of these. Briefly, we will look at Debezium and Kafka, and we'll spend a bit more time on Apache Pinot. So what is Apache Kafka? I think we are all here after current, so we do know what Kafka is. But very briefly, Kafka is a distributed commit log. We use it to build high performance data pipelines. Uh, as is the most common use case, we will use this as the central as the communication between our database and Apache Pinot. Debezium, how many of you are familiar with what Debezium is? Okay, so that's still a few people. Okay, so Debezium is a change data capture platform. And the way Debezium works is that it connects to your database. And as soon as there is an insert, update, or delete happening, it emits an event into Kafka, right? The way it does that is by reading either the bin log or the val log of your database. As we'll see in the example, these changes are transmitted instantaneously. So as soon as you insert a row or as soon as you update a row, that change gets emitted into Kafka, right? And finally, oh, but before we go to Pinot, I want to show you how Debezium works. The way Debezium works is by creating something called connectors. Debezium has connectors for various databases, Postgres, MySQL, Cassandra, and a whole bunch of others. So all of these databases can be monitored by Debezium in real time. If there is a change in the database, Debezium is going to ingest that into Kafka, and you can do things with them as soon as that data comes into Kafka. Okay, this is part of the Kafka Connect ecosystem, which is basically technology which lets you do common operations such as moving data into Kafka and moving data out of Kafka so that you do not have to write connectors on your own, right? So it's a well-established, matured framework that we are going to bank on to build a real-time data pipeline. I can't hear you. You just have to be a little bit louder. No, so Debezium is not a logging system. Debezium is change data capture. So any change that happens in the database, it captures that change and then it emits it into Kafka. Each and every change. Oh, by the way, I didn't say this, but if you have questions, just please feel free to raise your hand, interrupt me anytime you want. That is perfectly fine. Uh, yeah, all changes move in. So when you move, what do you mean by selective changes? You only want inserts and updates, but not the deletes? Oh, yes, you can do that. When you configure Debezium, you can tell Debezium that I only want this particular database and this particular table, or you can tell Debezium to monitor your entire database, all tables in all the schemas and databases. Yeah. Yes. Yes. So Kafka Connect allows you to do single message transformations, but those tend to be on the simpler side. So we will see one such transformation, which is basically routing data from a table into a topic of its own, right? So if you have an orders table, there will be an orders topic in Kafka that we will read from. But if you're thinking about massaging the data and doing something with it, I think you'd have to write your own Kafka consumer into that. Okay, so Apache Pinot. What is Apache Pinot? So Apache Pinot is a real-time distributed OLAP database that is built for low latency and high throughput analytics, which is perfect for user-facing analytical workloads. We will begin by looking at these three salient features: real-time, distributed, and OLAP, starting with real-time. So when we say something is real time, we are thinking about it in terms of these three features: latency, concurrency, and freshness. Latency is how long it takes to execute a query. Concurrency is how many queries we are handling per second. And freshness is how fresh our data is, how up to date our data is. So when you are using Apache Pinot, you can have latency as low as 10 milliseconds, just single digits or double digits millisecond, on queries per second as high as 100,000, and on data which is available for querying as soon as it is ingested. So Pinot allows you to do real-time queries on real-time data. So that was the first feature, real-time. Next is distributed. Pinot is built from the ground up to be a distributed database, which is in contrast to how our traditional relational databases work. So relational databases, they co-locate compute and storage. So if you have a box which is running, let's say Postgres, you have a certain amount of storage, you have a certain amount of disk. But in Pinot, you can vary these semi-independently so that you can have a cluster which is designed for the kind of workload it is that you're trying to handle. And finally, it is an OLAP database. So we all know what the difference between OLTP and OLAP is, but just as So co-locating compute and storage, that just means that you have a machine and that machine has a certain amount of disk and a certain amount of RAM that is associated with it. You can scale that up vertically and you can scale that up and you would have a bit more power in your machine. But in the case of Apache Pinot, everything is distributed and you can vary what you want so that your cluster is more geared towards the kind of workload it is that you're trying to handle. So Pinot has something called servers and Pinot has something called brokers. If you want more compute power, you can add more servers and you can let them have the kind of RAM and disk that you want, right? So you can scale those out. And as soon as you continue to scale those out, you can scale out the capacity that it is that you're looking for. Okay. Yeah. Okay. So we were here. Okay. So OLTP and OLAP. Pinot is an OLAP data store. All of the queries tend to be on the read heavy side. All of those queries tend to work on batch of rows, and those batches are aggregated into a single metric, sums, averages, and those kind of metrics. In contrast, OLTP data stores tend to be more transaction focused. They work on one entity at a time, and the workload tends to be more write heavy. Pinot is on the OLAP side, so the workload tends to be more read heavy. So what kind of use cases does Pinot enable? Where the first and foremost use case that Pinot enables is user-facing analytics, low latency user-facing analytics. So imagine you have a website or a mobile app and you want to display a chart in your application. Pinot is well suited to do that. You can build those charts and graphs and render those in your mobile apps or your website at very low latency. Similarly, you can build business intelligence dashboards. Uh, if your user-facing analytics are external, business BI dashboards tend to be more internal. Pinot also allows you to do ad hoc query exploration. It comes with a query console. So before you build your charts and graphs, if you want to analyze your data and slice and dice it by writing some custom queries, Pinot lets you do that. And finally, you can use it for anomaly detection because things are happening in real time. You can detect outliers in your data as and when they come into the system. So having talked about what Pinot does, we will look at some of the underlying concepts of Apache Pinot. Let's start with the data model. Pinot has a very simple data model. It is tables that are made up of rows and columns. We create tables not by writing a create table statement, but by writing a JSON configuration. We will see all of this when we get to the demo. And as soon as you have a table, you can query that in familiar SQL. So let's start with tables. The basic storage unit in Apache Pinot is a table. There are no limitations on the number of rows that you can have in a table. You can have an arbitrarily large number of rows in your table. And tables come in three types. One is a real-time table, an offline table, and a hybrid table. A real-time table is a table that ingests data from real-time sources, Kafka, Kinesis, Pulsar. If you have data which is stored, if you have data which is stored in these systems, we can ingest that into Apache Pinot and you can query that. Offline tables store data from batch sources. If you have files which are stored in blob stores like S3, you can periodically ingest those into Pinot and you can query those. And a hybrid table is a table which is a combination of real-time and offline sources. And when you define a column in Apache Pinot, columns again come in three types: a metric, a dimension, or a date time. A metric is something that you want to compute a mathematical function on, average sums, those kind of stuff. A dimension is something that you want to slice and dice by. And a date time as well. That is self-explanatory. It is just a date time column. Let's look at streaming ingestion. Pinot supports both streaming as well as batch ingestion, but for the sake of the demonstration, we will just focus on streaming ingestion. It is something that Pinot does very well. You can ingest data from Kafka, Kinesis, or Pulsar. And the general recipe for doing streaming ingestion in Apache Pinot is first, you will create the schema for your table. You will create the table from this particular schema. When you create this table, you will say, okay, this is where I'm going to get my data from, right? This is the Kafka broker. This is the Kafka topic. Hey, just ingest that data for me. And finally, you send this information to Pinot so that the table and the schema are created, right? This is slightly different from relational databases because the creating the schema and creating the table are basically the same thing, right? Like create table ABC brackets and you write the column name. Pinot is slightly different. Schema and the actual table are slightly different things. That is because from that same schema, you can create a hybrid table, which is just a combination of real-time and batch tables. Querying. Querying is pretty simple. Once you have data which is stored in a table, you can write SQL and you can derive insights from your data. Pinot ships with two query engines. The original query engine was called the single stage query engine, which allows you to run very simple queries, aggregation queries, no joins, no CTEs, no window functions, just simple aggregate queries. Then Pinot introduced multi-stage query engine. A multi-stage query engine allows you to write more complex queries. If you previously couldn't do joins, you can do joins now. And you can use CTEs, window functions, and all of the other goodness that comes with writing more complex SQL queries. And indexes. So indexes, Pinot ships with a whole bunch of different types of indexes that you can use to optimize your queries. What index it is that you want to use depends upon the kind of queries that you're trying to run. Here are just some of the indexes that Pinot supports: Bloom filter index, forward index, range index, and StarTree index, and inverted index. Uh, Pinot has, like, one of the USPs of Apache Pinot is the StarTree index, right? Very briefly, a StarTree index is a group by which is stored on disk and updated as data comes into the system, right? If you have, imagine, if you have a query which says select product ID, the date, sum of the amount, group by 1, 2. You can tell the StarTree index to come to basically run this query and store this data on disk, so that when you're rendering your analytics, you have the data which is ready for you to present to your customers. We will use the inverted index in our example to speed up the queries. We will see how to create that when we get to the demo. Upserts. Pinot has native support for upserts. If you're moving data from an OLTP system into an OLAP system, rows in your OLTP system are going to change, right? Still staying with the e-commerce example, if you have an order which is placed in the system, uh, that order is going to go through multiple phases. It is the order has been placed, it has been packed, it has been shipped, it has been delivered, and it is still that same entity. Those changes you would want to be reflected in your OLAP data store. Pinot lets you do that because it has native support for upserts. Upserts in Pinot come in two flavors. One is a full upsert where the entire row gets replaced, or it comes in the flavor of partial upsert where only selected columns are updated. We will use full upsert when we get to the demo. We will make a change in the row and we'll see that get reflected in Pinot instantaneously. Yes. So the question was, what is upsert during ingestion? Upsert during ingestion is, let's say you have a system, you have Postgres and it has a table called orders. That order has now been shipped. That row has changed. Debezium is monitoring that change. That change will get pushed into Kafka. That change would then be consumed by Pinot and the row in Pinot will be updated. So as soon as that change happens, Pinot consumes it. That is your ingestion phase. And that row would now have the latest state. So let's look at the design of the system. The design is actually pretty simple. So there is a database. Debezium monitors that database. Debezium writes those changes into Kafka. Pinot reads changes from Kafka, and then the user can write queries on the data that has been ingested. So what's the general recipe for using Debezium? That is fairly straightforward. You create a Debezium connector, you point it to the database, and you wait for it to emit rows into Kafka. It's that simple. What do we do with Pinot? We create a schema, we create a table, we send that table and schema information over to Pinot, and then we wait for it to ingest data from Kafka. So with that said, we will look at the demo. Okay, so I don't think this is visible. Is it visible to you guys? Not at all, right? This one? Okay. I think, oh, this is this visible, right? Okay, nice. So we will start by looking at what a Debezium connector configuration looks like. So it's actually pretty straightforward. It just requires some information about how to connect to the database and some miscellaneous information around, oh, it's still not visible? Yeah, let's wait for them to turn off the lights.
You can actually try clicking on view and focus on content.
Okay.
No, on the top, you can see views, right?
Oh, you mean the Teams window?
Yeah, correct.
Oh, I'm. Yeah, exactly. Much better. Okay, so this is the Debezium connector configuration. I'll just zoom out and then we'll zoom in back again. Okay, so the Debezium connector has, I know it's not legible, but we'll get there. It has a few parts. The first is us telling what kind of database we are connecting to, the credentials for connection, any transformations that we want to apply, information on how we want to communicate with Debezium once the connector is deployed. This is called Debezium signals. And just some miscellaneous other information such as any compression that you want to apply, etc., etc. So let's start at the top. Visible for you guys? Yes. Okay. We have a Postgres table. So a Postgres database. So we are going to tell Debezium and say, hey, we want a Postgres connector. Um, Everything is running in a Dockerized environment. So the host name is DB. I'm telling Debezium that, hey, um, connect to this particular server. Here's the username. Here's the password. And that's the DB that we should be connecting to. I have a very simple transformation. I'm telling Debezium that every single table that you ingest should go into a topic of its own. That's a regex router. What we've basically done is we've basically told Debezium that when you're extracting the name of the table, uh, when reading the data, just move every single table into a topic of its own. And this is the signal table. Signal tables in Debezium are basically used for telling Debezium to do miscellaneous things like running snapshots, right? Snapshots are just backfills. Once you deploy a connector, you can tell Debezium, hey, I have data which is already stored in the database. Could you please load all of the historical data into Kafka? And we will see an example of using a Debezium signal when we look at the demo. Now, having seen that, we'll look at what a Debezium message looks like. That is because this will be key when we start ingesting data into Pinot. We will store this message from Debezium completely and then extract information out of it. If you have questions, please feel free to ask. I'll pause here for a minute. Okay, so this is what Debezium's message looks like. Basically, it has schema for that particular table. It's a giant schema that says this is the row, this is the data type, and then it has the payload. The payload basically has the before and after state of the row. If it's an insert, there is no before row. It'll just have an after because the row is newly created. But if it was an update, you would have before and after, and it will give you the old and the new states of the row. For our example, we are only interested in the after payload. And what in this example, the after payload just shows an order that was placed in the system, right? We will take the after payload and we will store this in Pinot as a JSON, and we will extract fields out of it. And you will see why this is very helpful because it helps us evolve the schema. Because if a new row, if a new column is added into a table, that particular column will automatically become a part of the after payload. Okay. And you can simply extract that column out in Pinot and you don't have to run any backfills. It comes in the after payload. Yeah, before and after. The schema will change, but we don't really use schema for anything in when we are ingesting this data. The schema is helpful if you're using sync connectors that come with Kafka Connect. So if you were moving data from, let's say, MySQL to Postgres, you can have what is called a JDBC sync connector, and that would use the schema to automatically create tables and insert data into it. In our case, we're just going to use the after payload and just store it as it is in Pinot. It'll just be a JSON payload. It'll just be JSON. This JSON that you see is exactly what it'll look like in Kafka. I just ran a Kafka console consumer and got one message out. Yeah. Got it. So how do you deploy this into production? So Debezium ships with its own Docker image, and you can run this in your cluster. Let's say if you have an ECS or an EKS cluster, you can run Debezium images, and using its REST API, you can create connectors, and your Debezium instance should be able to connect to your database. Does that answer your question? Yeah. So Debezium, when I was talking to the core contributors of Debezium, they said that it can handle writes as high as 80K writes per second. So that should be fairly sufficient for a whole bunch of use cases. Single database, yes. Yeah. Yes. So Debezium connectors, they work differently depending on whether depending on what kind of database you're connecting to. So the MySQL connector works differently from the Postgres connector. So in MySQL, you can run one Debezium connector, and that can connect to all the logical MySQL databases. But if you're doing Postgres, you would need multiple connectors for multiple databases, right? Because as a part of your database credentials, you specify this is the database that I want to connect to.
One question here. Is there a flush interval associated with Debezium that you can configure?
I don't know, but as soon as you insert a row or update a row, that change is instantaneously moved by Debezium into Kafka. So I don't think there's a flush interval.
So are the messages getting batched in a micro batch and sent to Kafka, or each individual goes in separately?
As far as I understand, it is each individual row. Okay, so we've looked at Debezium configuration. We've looked at what Debezium message looks like. We will look at the orders schema. So this is what schema for a Pinot table looks like. Let me zoom this in. Okay, so we have a table which is going to be called orders. So the schema is called orders, and you define the three types of columns that you're going to store. You define the metric columns, the dimension columns, and the date time columns. I'll expand each one of these. We'll go over those, and then I'll collapse that section. So dimension fields, ID, which is the primary key for that particular table. Source is where we will store the message which is coming from Debezium. And we are going, as we will see, we will extract each one of the column that comes in the Debezium payload into a dedicated column of its own. So we just have a few columns for things that we want to extract out of that JSON payload, right? So it is the name, the data type of that particular column, and whether it handles null values or not. Similarly, metrics, the amount of that particular order is the metric that we would want to aggregate or find the min and max on. So the amount column from the table becomes a metric field in Pinot. And similarly, created at, updated at, and deleted at, Debezium sends date time columns over as milliseconds since epoch. So that's what we specified, that created at, updated at, and deleted at would come as milliseconds. And finally, this is just the primary key. We need this because we are going to run upserts. So Pinot needs a way to identify that, hey, this is the row that needs to change. Having seen the schema, we'll move over to tables. The table configuration in Pinot is a little bit more involved than writing the schema. Again, I will collapse the sections, and we'll go over each one of these. Okay, so we start by saying there is a table which is called orders. We say that this is a real-time table because we are going to ingest data from Kafka. Segments. Segments are basically shards. Pinot divides your table into segments, and these segments are spread over the data, spread over your entire cluster. So segment configuration just tells you how it is that you would like to create your segments. In the segment config, we've specified that we want to do a time-based segmentation. So by looking at the created at field, it is going to create the segments. You can also specify retention for your segment so that older data gets purged automatically from the Pinot cluster. Over here, we've specified that we want to keep the data for 365 days. The data which is 366 days old would automatically get purged from your system. You don't have to do anything for it. Yeah, and we can also specify indexes as a part of the table configuration. So imagine if you wanted to find how many people use Mozilla Firefox to place orders on your particular website or app. User agent is a part of the table. So if you want to run text queries, you can create text indexes and run full text search queries on a Pinot cluster. Similarly, we've specified other indexes as well. I mentioned that we were going to use the inverted index. Creating inverted index in Pinot is fairly simple. You just specify the name of the column on which you want to create the inverted index. Okay, understood. I will explain. So when you create a table in Postgres, right? When you run a statement such as create table ABC, open and close brackets, and you write the name of the column and the data type of that column, right? So the schema and the table are essentially the same thing. When you hit enter, the table gets created along with its schema. In Pinot, these are slightly dissociated. You create a schema, and from that schema, you can create both a real-time table and an offline table, right? So you can have data that is being ingested from files, let's say stored in S3, and you can simultaneously have data which is coming in from Kafka, right? Both of them look exactly the same because they are the exact same table. So the schema makes them look the same. The table configuration is slightly different because in one you would say data comes from Kafka, and the other you would say the data comes from S3, right? That's why you have schema and table schema configuration and table configuration as slightly different. Okay, back to table. This is how we create the inverted index. And this is the upsert configuration. This is where we specify that we are running a full upsert. And in the ingestion config, we specify which Kafka broker we want to connect to and which topic we would like to stream from. Again, this is Dockerized, so the broker is just Kafka 1992. And the name of the topic is orders because we told Debezium that orders table goes into orders topic. Scroll up. The what? $36. Load mode is mmap. Okay, so load mode is how it is that we would like to load data. Here we are saying just use mmap to load your data. And Pinot also allows you to run simple transformations on messages as they are being ingested. So in JSON, in the JSON that was generated by Debezium, there is an object called payload. We are going to write a very simple JSON path expression to extract the ID out because that is the primary key. So as soon as that data gets ingested, we want to extract the primary key out. Similarly, we extract the created at field because that is how we want our segments to be created. So we extract it directly from the after payload. Here we are storing the after payload itself. As I mentioned earlier, for being able to evolve the schema, we want the entire after payload to be stored in Pinot. And then after we have stored that after payload in the source column, we are going to extract fields out from the source column itself that way, if you have a new column, you don't have to run a backfill. You can just go to the source column, get the new field out, and start writing your queries. And Pinot also allows you to create data on the fly by applying simple transformations. So we know that created at was milliseconds since epoch. We can convert that into a date string, which is year, months, and day, by running the toDateTime function. Right? This is what the table configuration looks like. There is a REST API that we will use to send all of this information over to Pinot. Right? So let's look at the demo. So I've done some of these steps ahead of time. Like creating the data and storing that in Postgres. So we'll start by creating a Debezium connector, right? So the way you create a Debezium connector is that you take the Debezium connector configuration and you send it over to Kafka. You send it over to its container, right? There is a REST API. It'll accept the JSON payload and it will create a connector for us, right? So let's start with that. This is not going to be legible, is it? Nope. Yep. So this created a Debezium connector for us. Right. So Debezium just echoed back the connector configuration that we sent over. So everything that we just wrote in our JSON file just came back to us. That is Debezium's way of saying, hey, I've created a connector for you. Next, we will create a schema in Pinot. Again, you can do that by using a REST API. Let me, right? So I'm running this command in the in terminal below. Okay. It says orders schema was successfully added. Once the schema is created, we can create a table using that schema. So I'm going to run this particular command, curl command. And it says orders real-time table has successfully been created. So we said that our table was going to be real-time. The name of the table is the name that you give to the table, appended with whether it's real-time or offline. Okay. Next, we need to tell Debezium to backfill the data. You do that by using a Debezium signal. So Debezium signal is nothing but us writing a row in the signal table and telling Debezium like, okay, please run a backfill and load the historical data into Kafka. Okay, so here we are saying just write everything from the orders table into Kafka by running an incremental backfill. So this will take us to a SQL query, and let's run this. Okay. Let's look at what the signal table looks like. So this is the signal that we gave. Oh, man. Yeah, I don't think I can zoom this in. So okay. Basically, this is the signal that we gave Debezium, and the other rows are basically just telling us that Debezium acted upon that signal and loaded data into Kafka. So what we will do is we will go to the Pinot query console, right? We see 0. So this is initially what I had set up. There is 0 tables. When we refresh the page, we will see that there is a new table that has been created. Okay, that's the table that we created. Let's go to the query console. We created the orders table. Let's look at what that looks like. Okay, legible. Okay, good. So ID was the ID, the source was the entire after payload, and these are the columns that we extracted out of it, right? So the amount is 791, which has been extracted into a column of its own. But if you look at the source payload, you would see that the amount is 791, right? If you add more columns to the after payload, you can extract those out. That's as simple as updating the table configuration and the schema configuration. And finally, we will just run a query. We created the date column on the fly. So let's see what is the total amount of the orders that is being placed per day, right? This is familiar SQL. So select date, sum of the amount from orders, group by one, order by one. Very simple. And you run this query, you get your results back. And for January the 1st, 2024, this is the total amount of the orders that was placed. So this is basically a very simple recipe for how you can move data from your OLTP store into your OLAP store. Now, this data is static, but if this were a database where orders were being placed continuously, this value would keep changing in real time, right? So if you have a dashboard where you say, okay, this is my daily sum of the orders, a sum of the amount for all the orders that are placed, this query would return in milliseconds, right? So this is basically everything I have for you on how you can move data from an OLTP store into an OLAP store. If you have questions, please feel free to ask them. Yeah. You mean the JSON in? Oh, the schema and table configuration for Pinot? No, you have to handwrite those. You have to write those by hands. But once you set those up, I think you'd come to understand that it's actually fairly straightforward. You're just specifying where the data needs to come from and if you need any transformations on the data as it gets ingested. Yeah.
There's also Apache Druid, which is a very similar
Competitor. Yes.
Yeah. So just want to understand why is there a specific use case for Druid versus Pinot that you will highlight?
So I don't have a detailed comparison for you off the top of my head, but if you can come visit us on the Slack, we would be more than happy to talk to you about it. Can you use data on MongoDB? So that would still be moving data from a transactional store to a transactional store. I know MongoDB has the aggregation framework that that you can use, but in terms of performance and scale, I don't know how the two compare. Yeah, it's still at a transactional store. Pinot, on the other hand, is an OLAP store, so it's focused on running analytical queries. More questions? So the backfill that we ran was actually using Debezium signal. When you actually submit a signal to Debezium, if you have, let's say, data which is 10 years worth of data, but you only want to load 2 years worth of historical data, you can tell Debezium that, hey, please only load those 2 years and not everything in its entirety. You can write a where clause. What that tells Debezium is run the backfill in small batches, right? So the way Debezium does that is that it sorts your primary keys. And if, let's say, the batch size is 10,000, it'll load 10,000 rows, keep track of that, then the next 10,000 rows, then the next 10,000 rows. Yeah. Yeah. You'd have to be a little bit louder. Yeah.
Oh, okay. Yeah, just wondering, I also like following this iceberg hype in a way that you have for example, a source connector for iceberg tables into Pinot so that you can use your quick OLAP queries on iceberg stuff, for example, from Tableflow now.
So we don't have support for iceberg.
Yeah, that's...
No more questions? Okay, then that's it. That's all I have for you. Thank you so much for listening.